Ma, we're about 100.
100. And we have just 16 in the class. Okay. So, introduction to seismicity. I'm Dr. Oluwakemi Adogun. I believe you have been interacting with Dr. Alo, two of us. Have you started the class with Dr. Alo?
Yes, ma.
Yes, ma.
Or is this the first time that you'll be meeting for this course?
We've met twice, ma.
How many contacts?
2 times. One was online and one was physical.
Okay. So now, talking about seismicity, why do we have to learn about seismicity? Why? I believe the class is for both geology and geophysics. Am I on track?
Yes, ma.
Okay. So why do we have to learn about seismicity? Why is it? What's it all about? As geophysicists, as geologists. Geophysics has to do with application of physics to understand the structure and the working of the earth. Signals are sent into this to measure variation in physical properties. And this variation in physical properties can give us clue of what is happening around our environment. And it can help us to mitigate disasters. It can help us to be able to predict. It can enable us to improve our technology. In situations where we have earthquakes, what could be done? What is the magnitude of this earthquake? What is causing this earthquake? How can it be managed? It could lead to loss of properties, loss of lives, so many properties being damaged, billions of dollars being lost. What can be done to be able to uh, uh, prevent such natural occurrence? Geophysics can be divided into exploration geophysics and geodynamics. When we talk about exploration geophysics, it's the process of imaging what is inside the earth. Direct sampling with drilling can only reach around 10 kilometers, so in-depth methods are needed. It's not all the time that you have to drill. Various methods deployed and measurements could be taken. Often used to describe commercial exploration, but includes investigations to the depths of mantle and core. All geophysical methods can be divided into active and passive techniques. When we talk about active methods, that is when we let signals into the subsurface and we measure variation in the physical parameters. When we talk about passive techniques, we measure the natural fields, gravitational field, the magnetic field. What are these alterations? What can we deduce from these alterations? What can from them? So seismic studies, sound waves are generated with an explosion or an earthquake. There's this particular method, which is the seismic method, and what it entails is the use of caustic energy, generating acoustic energy, which is similar to that is experienced when it comes to earthquakes and seismicity. And like I've said, that they measure varying geophysical parameters. So examples of the geophysical methods, we have the gravity. What does it measure? Density variation. We have the magnetic. What does it measure? The magnetic susceptibility. We talk about the seismic. We have 2 types, the seismic refraction. We have the seismic reflection. I don't know if I'm audible. I hope you can hear me and I'm not too fast.
Yes, ma'am.
Okay, so we have the seismic refraction and we have the seismic reflection. We use refraction for near surface investigation, and we use a seismic reflection for deep surface investigation. When we talk about near surface investigation, it could be for groundwater exploration, it could be for engineering investigation. When you talk about seismic reflection for deep investigation, it could be for hydrocarbon exploration. When we send the signals into the subsurface, we use it to image the interior of the earth. And this can help us to delineate where we have abundance mineral resources. Okay, and once this has been discovered, it's a good source of income, way of generating income. We have the resistivity method that measures the resistivity variation of the subsurface. We have the spontaneous potential. It measures the potential differences. We have the induced magnetic method, ground penetrating radar, magnetodoric. What does it measure? It also measures the resistivity variation. So I've been able to itemize up to like 10 geophysical methods here. So when you're being asked about geophysical methods or geophysical tools, don't tell me that you only know resistivity, electrical resistivity method, you only know gravity method, magnetic method, okay, seismic method, and I've said that these geophysical methods could be classified into two, active and passive. We can even classify them as contact and non-contact. Contact in the sense that you want to take your measurements, your survey on the ground, you put your equipment on the ground before sending your signals into the subsurface. That is a contact. You have contact with the ground. So the non-contact method, you can use your airborne technique, use your aerocopter to survey the area to acquire your data, like your magnetic method, like your gravity method. You do not need so much personnel. All you just have to attach your equipment to the helicopter and it will survey the environment to get the hero data. Okay, so that is a non-contact method. You don't have to have contact with the ground before you are able to acquire your data. And it enables you to cover large expanse of land, area that might not even be accessible. With that, you can be able to cover it and you can be able to identify your area of anomaly. When you say your area of anomaly, that is where you have your deviation from your normal trend. What is the resistivity range in that area? Okay, and you are now seeing something extremely high. That is something must have triggered that. Okay, that's an anomaly, deviation from the normal trend. Okay, or you are having extremely low. Something must be responsible for that. Okay, and when you are interpreting, you don't interpret in isolation. You interpret relating to the geology of that environment. So that can I guide you. Okay, what is the history? What is the geology? What is the geological mapping of that area? What can we say about the kind of rocks that we have here? Is there basement complex? Is there sedimentary terrain? What can we say about that? What is associated with that? What kind of minerals are usually associated in that area? What kind of minerals are associated? That will give you a clue of what might be the cause of the anomaly. And when you have identified the area of anomaly, for instance, let's say from literature, it has been identified that we have hydrocarbon accumulation in University of Lagos, but you don't know where precisely in the University of Lagos. You carry out your reconnaissance survey using your magnetic method, using your gravity method. You now identify that Faculty of Science is where you have your anomaly. Okay, now you have identified that is where you have your anomaly. You have used a non-contact method, gravity method, magnetic method. You can now use a contact method, which is seismic. Okay, which can give you more detailed information. Take your energy into the subsurface and you study it. And that technique, that seismic method, has helped in discovering hydrocarbon. In fact, it was applied in the Niger Delta, and that is when we experienced the Hull boom. and there are a lot of exploitation. Okay, so that is the essence of research. Studying the seismicity, what causes it? It has to do with the sliding of this plate tectonics, okay, that brings about this earthquake. And when this comes into play, it can be disastrous. It can destroy so many cities. It can cause building collapse, destruction of fire services, so many things. Fire outbreak, related to fire outbreak, loss of lives and properties. But in the course of studying this activity, we discovered that we can even generate artificial sounds, artificial energy that can even help us to even discover mineral resources, and which has been applied. When we talk about geophysical tools, we use them for different things. Just like we can use it for hydrocarbon exploration, which I've explained. We can use it for regional geological studies, exploration of mineral deposits, engineering site investigations, hydrogeological studies. What do you mean by hydrocarbon exploration? Just like I've said, oil and gas sector, discovering hydrocarbon accumulation. Regional studies, knowing the kind of rocks that we have in that area, the associated minerals, exploration of mineral deposits, okay, carrying it out to know areas where we have these deposits, and further carry out investigation to know the estimates. Because if you even have this mineral deposits, what is the quantity that we have? Is it commercially viable? If we exploit it, are we going to make profit at the end of the day? Does it worth investing? So all that has to be put into consideration. Talking about engineering site investigation, you want to put up structures, okay? You want to put a skyscraper. How competent is that soil to support that structure? If the soil is not strong enough to support kind of structure, it can lead to building collapse. So you have to know, carry out investigation to know the kind of methodologies, the variation in this materials beneath the surface, which can inform the kind of materials that you use to reinforce. Okay, it can guide the building design. It can determine the kind of foundation. Is foundation is a deep foundation that will be able to support the proposed structure. All these scientific methods could help us. Studying of contaminants, mapping of the level of contamination. Your groundwater is contaminated. Our geophysical method can be able to identify, to eliminate, to know the extent of contamination, thereby knowing the kind of remedial process that can be put into place to ensure continuous clean supply of potable water. Okay, we have buried metallic objects. We can use our geophysical methods to be able to identify, to locate regions. We have storage tanks beneath the surface. You don't even know where it is. You have leaking pipes. You want to identify where the location is. You can use our geophysical tools, and it will help us to identify where we have this area of anomaly. We have the archaeogeophysics. You want to locate where we have dead remain bodies over so many years. Our geophysical tools can help us. We have forensic geophysics. That forensic geophysics talks about when you have that can help us resolve crime issues. Okay, indiscriminate burying of bodies. All these yahoo girlfriends going to their houses, killing girls. Just burying them anyhow. You can cite it, but you might not be able to locate where precisely the body has been buried. But with the geophysical tools, we can be able to image the subsurface and be able to identify where we have the area of anomaly. It's most likely this is the spot where the body is being buried. That means it has helped us in crime issue. Okay, so it can help us. That an aspect of forensic geophysics. So in a passive technique, a natural occurring signal is detected, e.g. pull of gravity of a buried So that's what I'm saying. The passive method is gravitating signals into the source of it, like our electrical resistivity method, our seismic method of it. What plate motion? What happens to all these mountains? This depends heavily on information derived from this geophysical imaging. Due to the gliding of the plates, movement, sliding, and all that we have all these tectonic activities bringing about this earthquake. So talking about the interior of the earth, we have the crust, we have our mantle, we have our outer core, we have the inner core. The crust is mainly silicate minerals enriched in lighter elements like sodium. We have our mantle, which is silicate minerals with more heavy elements like iron and magnesium, divided into the upper and the lower mantle. We have the outer core, which is a liquid iron that converts rapidly. We have the inner core, which is a lump of solid iron, roughly the size of the moon. We have the crust and the mantle, are defined in terms of the distinct chemical compositions. The lithosphere and the artesosphere. The lithosphere is the rigid outer part of the earth, typically about 100 to 200 kilometers thick, and includes the crust and the uppermost mantle. We have the lithosphere. So they are defined in terms of the mechanical properties. So when you talk about seismicity, this seismic hazard is uncertain in most of the situations and is posed by the sizes of the magnitude. During the time of Sodom and Gomorrah, there was they believed that they prayed, and because they prayed, the ground shook. There was opening, there was earthquake, and all that. That is spiritual. But as scientists, there was earthquake, and we know that it's not the prayer that must have caused the earthquake. The scientists believe is as a result of the tectonic activities, the plates and all that must have resulted to the earthquake that really occurred. And that has really made scientists to find out what could be done. We need to study this earthquake. The effect could be devastating. If we can predict when it will occur, we can evacuate people and take them to somewhere that is safe. Okay? If we can predict, we can be able to know the magnitude. Is it going to be like 5? Is it going to be like 7? Is it going to, that will enable us to determine how catastrophic it could be. Okay, and what kind of remedial process can be put into it. It helps in building design codes, improve technology to see even when these buildings, when they move and all that, what could be done that the building can be able to resist it to prevent collapse of structures. So then and another aspect is the sense is uncertain in most of the situation and is posed by sizes of the magnitude of potentially damaging earthquakes occurring at multiple locations. This non-uniformity of can be observed from varied trends of the past earthquake, that has happened in the past. And, it's of great concern. And it's, because of the devastating effect that it can have, resulting in the destruction of so many things. So talking about the seismicity, there are some activities that can also bring about, that can trigger the fracking, breaking of this rocks. It can trigger it. An earthquake is a sudden rapid caused by the breaking and shifting of tectonic plates beneath the Earth's surface. So this shaking can cause the collapse of buildings and bridges. It can cause disruptions in gas, electric, phone services. It can trigger landslides, avalanche, flash floods, fires, huge destructive ocean waves like in tsunamis, and structures constructed on unconsolidated landfill, old waterways, and other unstable soils are generally at risk unless seismic mitigation has been put into place. So you can see it can result to collapse of buildings, and all this are happening simultaneously. Destruction in gas, electric, phone services, you cannot connect with anybody, buildings falling, uh, fire outbreak, everything happening at the same time. So our seismicity is not controlled by climate, it's not climate dependent. It can occur any time of the day, but it's as a result of the breaking and shifting of the tectonic plates. And this could be very hazardous. Just like what happened in Northridge, California in 1994, it resulted to about $7 billion, to correct what really happened. Can you imagine? So you can see the devastation. Can you imagine that huge amount of money, loss of lives and properties, the damage. The best known gauge of earthquake intensity is the Richter magnitude scale. We have the Richter magnitude scale, which can be used to measure the magnitude. Okay, when you have like 7, 6, they are considered to be very high, even from 5. Okay, and we use a seismometer to detect it, to measure it. But when we have like 2.0 magnitude, it is considered to be slight, to be mild. Okay, but greater than 7.0 may destroy many buildings. The number of earthquakes increases sharply with every decrease in Richter magnitude by 1 unit. For example, there are 8 times as many quakes with magnitude 4.0 as there are with magnitude 5.0. So large earthquakes are customarily reported on Richter scale. So scientists prefer to describe earthquakes greater than 7. When we now have the one greater than 7, we can use moment magnitude scale. What triggers pressure, change in weight, vibrations. Vibrations can trigger earthquake. And studying this earthquake, we can be able to come up with seismic mitigation policies. Seismic mitigation policies, such as building codes, okay, site section of public structures, how to build. It can guide the kind of materials that could be used to build, to be able to resist all this collapse, So, such as what has been done in Portugal. They have seismic resistant construction techniques which they adopt and which have been known as the Pompililo, which has been working for them. This is also a deadliest earthquake on record that occurred in 1956. It was catastrophic, killing about 830,000 people. The magnitude is approximately 8. So it occurred January 23, 1956 in China. About 830,000 people died. So you can imagine, if we can lose that huge amount, huge number of people, 830,000, that is huge, with loss of properties. Don't you think it's worth researching? Don't you think that it really was studying to be able to predict, to be able to prevent, to be able to avoid, to be able to come with policy that will be favorable? That is one of the reasons why we have to study these earthquakes, study the seismicity, how to improve our lives, save our properties, save our resources, also apply the knowledge in exploring for mineral resources. That is why I said in the course of studying this seismicity, earthquakes, seismometer was developed, and from there we then have our seismograph. We use our seismograph now to now study our seismic waves. Okay, when our seismic waves are being generated, they are being received, they are every time being saved on our receivers, the geophones, and these signals could be displayed on the seismograph, where we can see them, be able to analyze them, retrieve it, process it, and be able to make inferences, and from which mineral resources could be explored. All this as a result of studying this seismicity and earthquakes. Okay, so before we proceed, I want to ask, why do we have to study seismicity? Why do we have to talk about earthquakes? Why? Is there any passion or anything that is really driving us to really study this? Feedback, please. Okay. So apart from that, to predict and to know the magnitude of the effect that it can have in a particular area, that is one. Which other reason do you think we need to study this earthquakes and seismicity in our environment? I want more comments. We can use a chat, please. I'm waiting, please. We'll learn the structure of the head, okay? The advantages, yes. We'll know about it. We'll be able to predict about it. So what are the other things that comes into play? I have 45 here. I don't expect, okay, I'm listening.
Okay, so we learn seismicity to set, to build, to know, to build in, to know foundations that can resist earthquake disturbance.
Okay, it can help us in our building designs. Yes, building codes. Beautiful. Okay. I'm waiting. More comments? Somebody said for us to be able to predict and to be able to know the magnitude so that we can know the catastrophic effect that it could cause. Somebody said that it could help us in making our building design codes. Beautiful. More comments, please. Yes, save lives and properties. Save lives and properties. You can imagine 830,000 people dying, almost 1 million as a result of earthquakes, cutting across 6 states, running to $7 billion. You can imagine the kind of development that kind of money could be used for. Saving lives. Lives, very, very important. That's the most important thing. Saving lives and properties, beautiful. More comments? Then another one that somebody said, mineral exploration. Yes. So apart from, in the course of studying it now, they've also developed, okay, that we can even generate acoustic energy. And this acoustic energy, through the process, through the geophysical method known as seismic method, you can be able to even detect mineral resources. You could use it for engineering investigation. We could use it for water investigation and which is applicable and generating resources, generating income for the government. So that is a beautiful one too. It helps to manage risk, yes. Come up with policies, understanding the earthquake hazards and how to manage it, okay? Coming up with policies that will favor the masses, okay? So I talked about geophysical methods. I mentioned the geophysical methods. We have various geophysical methods that could be used for exploration. So waiting for comments. Geophysical methods. I mentioned 10 geophysical methods. So geophysical methods. Seismic. Okay. Geophysical methods, I'm waiting. Mention the geophysical methods. Some of the geophysical methods that could be applied to image subsurface. Okay, resistivity method, seismic method, gravity. That's 3. I have bonuses for those that are responding to questions. So if you don't like 1 mark, 2 marks. Spontaneous potential method, beautiful. Electromagnetic, right? Resistivity methods, magnetic method. Which one is DPR? DPR. Ground penetrating method. Ground penetrating radar. Okay, beautiful. Which other one? Magnetoloric, beautiful. Okay, is that all? We have the geometric method. We also have well-logged data, continuous measurements of variation in physical parameters along the borehole. That is also very important. Your well-logged data, also very important. Beautiful. All these tools, all these techniques could be used for various things. Tell me some of the things that they can help us to achieve. Applications. Applications. What can we use them to do? Scientific research and advancement, right? Tectonic movements, okay? Determine subsurface materials. What do you mean by subsurface materials? Mineral exploitation, beautiful. Mineral exploitation. Varying density across the Earth's surface, which could lead to discovery of hydrocarbon accumulation. That's hydrocarbon exploitation or hydrocarbon exploration, your oil and gas. Check anomalies in the subsurface. What are the anomalies that you're looking for in the subsurface? There must be a target. Why you're looking for the anomaly? Groundwater exploitation, groundwater exploration, regional studies, yes. Regional studies, subsurface mapping, beautiful. Location of buried pipes. Okay, location of buried pipes. I'm giving you clue. More. Aquifers. Aquifers is still groundwater. Buried structures. Okay. What else? What about environmental studies? That's contamination. Environmental studies. Okay. What about the building? You're not talking about that. archaeological studies. Yes, mapping of the ocean floor for us to know where to place our cables. We take measurements, construction of bridges, construction of dams. Yes, we carry out our investigation for forensic, yes, forensic studies. Okay, beautiful, beautiful. Okay, so we can proceed. So during a severe earthquake, occupants and building contents will be shaken. Items not properly secured may fall. Desk, furniture might slide. Filing cabinets, bookcases might topple. Ceiling tiles may be dislodged. Windows may crack, shatter. Sprinkler heads may shear off, result in water discharge. So there are a lot of things. Seismic device may cause building elevators to go to the nearest floor in the direction of travel. Stop. It might stop. Automatically open elevator, open car doors, season several operations, automatic fire detection, alarm going everywhere, reporting equipment may produce multiple false alarms going everywhere, is in array. Electrical power may be disrupted, no light, everybody in the total darkness. Lights may go off, telephone system, everything damaged. Shortly after the shaking has stopped, the deluge with cause, falling objects, those are the things associated with earthquakes, seismicity, and all that. There will be chaos everywhere, and as a result, people are already disturbed. They don't even know what is happening, leading to loss of lives and properties. So, but it is very essential that we study it for seismic risk analysis. Okay, this will expand our scientific knowledge and quantification of the hazard, the vulnerability, and the exposure. So this will give us idea of how to improve our technology and to, mitigate this kind of occurrences. So like I've said, the various geophysical surveying methods have been and are used on land, offshore. Each of these methods measures something that is related to subsurface rocks and their geologic configurations. Rocks and minerals in the earth vary in several ways. Exploration for oil and gas has been and ongoing in the Niger Delta Basin. Various tools have been used by past researchers to study its sedimentology, stratigraphy, economic prospects, and so on and so forth. And the biggest breakthrough in the petroleum and natural gas exploration came through the use of the seismic method. Magnetic and gravity methods are used for reconnaissance surveys to delineate areas of interest. For our seismic method, it comprises of two branches, the reflection and the refraction methods. In seismic surveying, seismic waves are propagated through the Earth's interior, and travel times of the waves that return to the surface are measured after refraction or reflection at geological boundaries within the ground. These travel times may be converted to depth values. Hence, the distribution of the subsurface interface of the geological interest may be systematically mapped. This represents a natural development of the already long-established methods of earthquake seismology, in which the travel times of the earthquake waves are recorded at the seismological observatories and are used to derive information on the internal structure of the earth. When we talk about our seismic method, our source is very, very important. We have our source and we have the receivers. Okay? It's a simple concept. Our energy source, depending on the environment, are we carrying out our acquisition on land or is it offshore? Okay, we have a source. What is the depth of penetration? It determines the source. To what depth do you want to investigate? do you want to assess? Is it to about 10 kilometers? Okay. Is it just 100 meters? 100 meters, that's shallow investigation, near surface investigation. So with the help of our sledgehammer, striking a metallic plate, you can be able to generate acoustic energy, sound energy. And that energy will propagate into the subsurface. So that is our source. And we can see radiating in all directions the energy generated. As it's propagating through the subsurface, it travels to the interior of the earth. And when it strikes a lithologic boundary, where there's abstract change in the density, there'll be change in the propagating velocity of this traveling wave. So when it strikes the lithologic boundary, what happens? It gets reflected and it gets refracted. Okay? You can see the pathway of the reflection and the pathway for the refraction. Our V1 telling us that it is propagating with the velocity 1. In the second medium, it is propagating with velocity 2. As it strikes the lithologic boundary and it gets reflected or refracted, it will be picked by the receiver. The arrival time of the signal will be picked by the receiver. Our receiver on the land is our geophones, while in the marine environment, we have our hydrophones. What the geophones measures is the ground motion, while for the hydrophones, the pressure difference. Okay. When we talk about our active source, this is for the reflection. You can see about 2.3 kilometers to show the depth of investigation. We could make use of our explosive, such as a dynamite, a shot hole with a dog, and the explosive will be detonated, and the acoustic energy, is generated, and it propagates into the subsurface. And as it encounters the lithologic boundary, it gets reflected, and the arrival time will be recorded by our geophones. And these signals could be displayed on our seismograph. And you can see we have the arrays of geophones, and these geophones are connected with cables. Okay, they are connected with cables, and this data generated could be retrieved, and a software will be used to process it to generate the image of the subsurface. And from there, interpretations, identifying associated features that could be related to certain mineral deposits will be identified. And these can now guide us where to drill to confirm the kind of minerals that we have there. Further investigation will be carried out to estimate what quantity of hydrocarbons, what quantity of minerals do we have there, is it commercially available, and that will inform the decision that will be made. It's not all the time. It's not even use of vibrosis stroke is more eco-friendly than using of dynamite, and it can even you can control the interval of generating your acoustic energy, the interval, the frequency. That is the short point. Okay, and when it is being detonated, what happens? It travels down to the subsurface, it strikes the lithologic boundary, it gets reflected, and we have our receiving point here, where the arrival time will be recorded. Okay, receiver vehicle with geophones. Okay, the information will be retrieved and be analyzed. So you can see the first layer, you can see the second layer. If you are being asked that you should discuss, you should explain the concept of seismic method, you should be able to explain, you should be able to illustrate. And when you illustrate, you must ensure that you label. You must ensure you indicate your arrow. You must ensure to tell us that it is the first medium, the second medium. You must be able to tell us duration. There is contrast in the density, there is contrast in the velocity, there is change in the propagating velocity. When you talk about our seismic, basically, we talk about two waves. okay, are seismic waves. We talk about the body waves and we talk about the surface waves. For the body waves, we have the shear wave. The shear wave is also known as the transverse wave. Then we have the compressional wave. The compressional wave is also known as longitudinal wave, and it's also known as the P wave, primary wave. It is faster than the shear wave. The shear wave is also known as the S wave. Okay, so for the body waves, we have the S wave and we have the P wave. You can call it S shear wave or secondary wave, P wave, the primary wave, or the compressional wave, longitudinal wave. Okay. Then we have the surface waves. The major difference between the body waves and the surface waves is that the body waves travels to the interior of the head. But when you talk about the surface wave, it travels along the surface of the medium. Examples of the surface waves are the Rayleigh wave, the love wave, and the Stoney wave. Example of the body wave, I've talked about it, the shear wave and the longitudinal wave. The differences between the shear wave and the longitudinal wave. The shear wave is a secondary wave. The longitudinal wave is a primary wave. It travels faster than the shear wave. The longitudinal wave travels through solid, liquid, and gas, while the shear wave travels through the solid. Okay, and the propagation. The compressional wave is produced perpendicularly to the source of production, where for the longitudinal wave, it travels in the direction of production. All materials have some degree of elasticity, but rubber, for example, is more elastic than metal or wood. The elasticity is the consign of forces acting between atoms and molecules in all materials. These forces keep individual atoms at constant distance in positions at which the potential energy of atoms is minimal. They are called equilibrium positions. If you apply an external force to a given material, we have moved atoms from their equilibrium positions. After removing the force, atoms in elastic materials return to their original position. When you talk about our head, it behaves elastic. But when force is being applied, and when it is being removed, you will not even know that anything must have occurred or not. I want to talk about wave. We transfer energy. We transfer energy from one place to another without any permanent displacement of the medium itself. So when you talk about this seismic wave, there are some properties associated with the wave. Okay, and there are also some terms that we need to know about this wave. Okay, and when you talk about seismic methods, it enables us to generate these elastic properties. Elastic properties such as our Young modulus, our Poisson's ratio, our Bock modulus, our Bock modulus, and our Exer modulus. So all these properties can enable us to determine the strength of the soil, the elasticity, the ability to withstand stress. And all this is applied when it comes to engineering investigation. Okay? So it's a physical property of a material which allows it to retain its original shape after the stress that caused the deformation is no longer applied. Our stress is force per unit area, where the strain is a change. The change, when the force is applied, there will be extension or contraction. There will be change. Okay, but when the force is applied, what happens? It might be able to regain its initial position, provided the elastic limit is not exceeded. Once it is exceeded, then what happens? It might not be able to gain its original position again. So when you talk about a wave, it's a disturbance and it transfers energy from one point to another usually without permanent displacement of the particles of the medium. It can be thought of as a disturbance or oscillation that travels through space-time, accompanied by transfer of energy. The direction of a wave propagates is perpendicular to the direction it oscillates. That's talking about different types of waves. We can define our wave in terms of, does it require a material medium for propagation, or it does not require material medium for propagation? When it requires material medium for propagation, we have the mechanical waves. If it does not require, we have the electromagnetic waves. So we can say we have two types of waves, the mechanical waves and the electromagnetic waves. But talking about the seismic waves, we talk about the body waves, and we talk about the surface waves, okay? But generally, we have the mechanical waves and we have the electromagnetic waves. So mechanical waves could be transverse or longitudinal, while our electromagnetic waves, they are transverse waves. Electromagnetic waves, such as your radio waves, your X-rays, your light rays, they travel with the speed of light and do not require a material medium for propagation. Your mechanical waves, like your ripples or the water, strings, musical strings, okay, they require a material medium for propagation. Like I've told you, that our compressional wave, which is the P wave, can travel through solid, liquid, and gas, and that is what is used when it comes to hydrocarbon exploration. We use our compressional wave velocity. And mostly for engineering investigation, we use our shear wave velocity. Okay, and I said our shear is good, it transmits in solid. Some of the terms, describing our wave, we have the wavelets, that is crest to crest or trough to trough, the speed of propagation, the amplitude, that's the maximum displacement for rest, direction of propagation, the axis along the travel time and all that. So we have the period, that's the time required for a complete circle, okay? And the frequency, that's the number of circles that you can complete in 1 second. The units of these quantities and their symbols. Then the equation of the wave. Your wave number, your angular frequency, and so on. Then talking about some of the properties of the wave, the refraction. So there's the phenomenon of a wave changing its speed. This means that the size of the phase velocity changes. It occurs when a wave passes from one medium into another medium. Okay, so this means that the size of the phase velocity changes. Typically, refraction occurs when a wave passes from one medium into another medium. The amount by which a wave is refracted by a material is given by the refractive index of the material. The directions of incidence and the refraction are related to the refractive indices of the two materials according to Snell's law. So Snell's law is a law that guides this seismic method. Okay, our wave moving from one medium to another. And we also have the law of reflection that tells us that the incident wave, the normal, and the reflected wave all lies on the same plane. And it tells us that the angle of incidence equals to the angle of reflection. Okay, that is the law of reflection. Then talking about the Snell's law, that tells us that the ratio of the sine of the angle of incidence to the sine of angle of refraction equals to the refractive index. Okay, so as the wave travels from one medium to another medium, there's a change, either the bending away or the moving due to variation in the density of the media. Okay, so and we can see there being designated as medium 1, medium 2. So the reflection, we have said that the angle of the incident, the reflected, the refracted rays, and the normal all lie on the same plane, and the angle of incidence equals to the angle of reflection. And that's what happens when it strikes a lithologic boundary and it gets reflected. And our geophones helps us to peak, to record the arrival time. Then we'll talk about the absorption. I said if the energy is being detonated and it travels down to the subsurface. For instance, you want to image about 2 kilometers and you are using striking hammer on a metallic plate. So definitely the energy will be attenuated and it will have been absorbed. It cannot get about 2 kilometers. Okay, that means absorption is a property. It gets attenuated, the sound will have been absorbed. So it's a kind of wave strikes a matter, it will be absorbed by the matter. When a wave with that same natural frequency impedes upon an atom, when the electrons of that atom will be set into vibrational motion, if a wave of a given frequency strikes a material with electrons have a same vibrational frequency, then those electrons will absorb the energy of the wave and transform it into vibrational motion. So that's another property of the wave. It could be absorbed. Then we have the diffraction, ability to pass through slits or bend to spread out. So diffraction occurs using light as a phenomenon. Light wave passes by a corner or through an opening or slit that is physically the approximate size or even smaller than that of light wavelets. So this is a special case of light scattering in which an object with regular repeating features, such as diffraction granting, produces an orderly diffraction of light in a diffraction pattern. The diffraction phenomenon is described as the apparent bending. So the apparent bending of the waves around that small obstacle and spreading out of the waves. You can see it's spreading out through that small slit, in all directions. So another property is the interference. Okay, when the waves are traveling with the same frequency, same amplitude at the superimposed, then we can have constructive interference. But once out of phase, okay, and it superimposes, what happens? We have destructive interference. So that is another one where we have constructive interference. We have increased resultant amplitude that is bigger. Okay, but when it is destructive, it is flat, zero. Then another property is the polarization. So ability to be able to constrain it to a particular direction. Light, the energy, acoustic energy can vibrate in all directions. Those that are vibrating in one direction in a single plane, such as down, are called polarized. Those that are vibrating in more than one direction, they are said to be unpolarized. So to polarize a wave, one can transmit it using the use of a polarized filter, so which will help us to constrain it to only one direction. So another phenomenon is the dispersion, where a wave undergoes dispersion when either the phase velocity or the group velocity depends on the wave frequency. And this could be illustrated using the white light, which was an experiment that was performed by Isaac Newton, using the light and prism. And this shows that light consists of several colors, and these colors cannot be decomposed by any further. So we can see it here as the figure exhibits the dispersion of the light between the Roy view. Okay, so when we image the subsurface, for us, what are the components that is essential for our data acquisition, for seismic data acquisition? I want you to respond. What are the essential components that are important for seismic data acquisition? I'm listening. Feedback, please. The essential components needed for seismic data acquisition. Essential components needed for seismic data acquisition. I'm listening, please. I said the essential components needed for seismic data acquisition. Yeah? What are you transmitting? Eh. Photo transmit. Oh, ni generate. Eh? You're not thinking about that. So what's the first thing? The source. The source. Yes, you have the source. What is your source? Do you get it now? Your source could be your dynamite, it could be your air gun. You use air gun for marine environments. You read more about different ways of generating the acoustic energy. You get there are different means of generating weight drop. You can use weight drop, you know, dropping it at various heights to generate acoustic energy. So different means, okay, of generating. So the source. And what determines is the source is your depth of investigation. To what depth do you want to investigate? So that will determine the kind of acoustic energy because of the intensity of the acoustic energy that you want to be generated. So that it will not be attenuated, it will be able to penetrate to the depth of your investigation. So your source is very important. Okay, I'm listening. You have mentioned one.
But we need
Huh?
seismic receivers like your geo,
Okay, we need our receivers. Okay,
like
what
your
are
geo.
they receiving? Yes, like our geophones, like their hydrophones. What are they recording?
But they are recording pressure changes or ground motion.
They are recording the arrival time. The time it takes the wave to travel to the subsurface, strikes the lithologic boundary, then come back. What time? It is recorded in milliseconds. It is recording the arrival time. Just like your echo sounder. Okay? You send the signal into the to determine the depth of the sea, the sea floor, the seabed. You generate your sound energy, it goes down, strikes the bottom, gets reflected back. You know your velocity, you know your time, then you can be able to determine the depth. Do you get it now? What it records is the arrival time. Is the arrival time, the time it takes the wave to travel from the surface to strike the lithologic boundary and get reflected back to the geophones. So it's the time in milliseconds. It's the arrival time that is being recorded. And the signal will be on your seismograph. Okay? Am I communicating?
Yes, ma'am.
Okay, so I'm listening. What are the components needed for the seismic data acquisition? Somebody said the
Yes,
source.
ma'am.
Somebody said we need the receivers, which could be our hydrophones, which could be our geophones. What else? Is that all? Okay. Is that all? I'm listening. No. We have only mentioned two. Eh, the plan, the design is the layout. Okay, it's part of it. You have to know your layout, know the location, where your source should be, where your offsets should be, where your geophones should be implanted. Okay, what else? What else? What else? Mention five. Oh, you have only mentioned two. You said the source. You said the receivers. The layout, okay, knowing how to place our, okay, So what else? I think the processing. We answered acquisition, seismic acquisition. The we are still acquiring. I think lost to the processing. Let me help you. So what else can you see? What else can you see? Oh, yes, the data storage. Okay, you have your data storage on your seismograph. Your seismograph. That is where you retrieve your data from. The seismic transmitter. What do you mean by seismic transmitter? Yeah? We have the cables, the connecting cables. We can have up to like 50 geophones. We can have up to 120 geophones. All those geophones, they'll be connected. They are connected with cables. Okay. So we have your source, we have your receivers, we have your storing cables. Okay. Connecting cables. Then you have your layout. Like somebody has said, yes, the layout. How you want to act like of properties of waves that we discussed today. The properties of waves that we discussed today. Waiting for your feedbacks. Okay. Absorption, dispersion, and so on and so forth. Okay. So what did we discussed again? We talked about the properties, and apart from the properties, what did we talk about again? Yeah, we talk about the seismic waves. So can you tell me the seismic waves that we have? Body waves. What's the okay? Yes, I'm listening. Yeah, the compressional wave. Yes, and the shear wave. Okay, compressional. And the major difference. You can tell us the major difference. The major difference between the body waves and the surface waves. The difference between the body waves and the surface waves. I want it ready. The difference between the body waves and the surface waves.
That's right. The body waves travel through the earth, while the surface waves travel along the earth's surface.
Along the medium, travels along the surface of the medium. Okay. Okay. So I think we can call it a day, right? So we'll continue from there at the next class. Is that okay for us?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So when will our next class be?
On
Can we have
Tuesday.
it like Tuesday?
You said?
Man, can
On
we have at the
Tuesday,
same time?
ma'am.
Like, guy, Dave, do you know the timetable? Why are you saying Tuesday?
Coming at the go now.
No, now why are you saying Tuesday? Do you know what's on the timetable? What if it's clashing with that subject? Man, we will get back to you through the crossword, man.
The last time we did online was on Tuesday.
Okay,
GPS
Guy.
123.
Yes, man, we'll get
the
back to
class
you.
rep will reach out.
Yes, ma'am.
Hello. So the class rep will reach out to me so that
Okay,
we
ma'am.
get across. Okay, thank you.
Yes, ma'am.
Yes.
In sense, right?
Let me update the slide and I'll release the slides, okay?
Okay, ma'am.
Okay, ma'am.
Okay, ma'am. Thank you, ma'am.
Yeah. Okay, you're welcome.